What if the universe, the vast, sprawling cosmos we call home, was silently preparing its own destruction? Picture this: galaxies, those glittering islands of stars and planets wrenched apart by an invisible force. Stars blinking out of existence, not with a bang but a whisper. Space itself, the very fabric of reality, stretching until it tears at the seams. This isn't the plot of a sci-fi blockbuster. It's a real scientific possibility known as phantom energy, one of the most unsettling mysteries in modern cosmology. And today, we're diving deep into the heart of this cosmic enigma, uncovering what it could mean for the ultimate fate of everything we know. The idea that the universe might end isn't new. Scientists have speculated about its demise for decades, from the fiery collapse of the Big Crunch to the slow fade of heat death. But phantom energy presents something far more violent, far more abrupt. Imagine an unstoppable force woven into the fabric of space, accelerating the expansion of the universe faster and faster until not even atoms can hold themselves together. It's a scenario so extreme that it defies our everyday intuition, yet the math behind it is chillingly precise. Could this really happen? Is our universe destined to rip itself apart in a catastrophic event cosmologists call the Big Rip? The answers lie in the shadows of our understanding, where cutting-edge research meets the edges of the unknown. Over the next few minutes, we'll unravel the science behind phantom energy, what it is, how it works, and why some of the minds in physics take it seriously. We'll sift through the evidence, from the way distant galaxies are moving to the subtle fingerprints left in the cosmic microwave background. And perhaps most hauntingly, we'll confront what this means for the future, not just of stars and planets, but of time itself. This isn't just a story about the universe's end. It's a story about how much we still have left to discover, and how fragile our cosmic home might truly be. So let's begin. Phantom energy isn't just another mysterious force lurking in the cosmos. It's a theoretical that could rewrite the rules of the universe's demise. To understand why, we need to start with dark energy, the better-known culprit behind the accelerating expansion of space. Dark energy behaves like a steady push, gently stretching the fabric of the universe over time. But phantom energy, it's dark energy's unpredictable cousin, growing more potent as space expands, like a snowball rolling downhill, gathering speed and size until it becomes unstoppable. This is where things get eerie. If phantom energy exists, it wouldn't just speed up cosmic expansion, it would escalate exponentially. Picture a rubber band being stretched. At first it resists, but if you keep pulling with ever-increasing force, the fibers fray, then snap. Now replace that rubber band with spacetime itself. Galaxies would first drift apart, then vanish over the horizon of visibility. Stars would be ripped from their galaxies, planets torn from their orbits. Eventually, even atoms, the building blocks of matter, would be shredded as the space between particles expands faster than the forces holding them together can compensate. The universe wouldn't just fade away, it would unravel violently in a final, catastrophic instant scientists call the Big Rip. The idea emerged in the early 2000s, when cosmologists studying distant supernovae noticed something peculiar. The universe's expansion wasn't just accelerating, it appeared to be doing so faster than expected, as if some unseen influence was turning up the dial. Phantom energy became a possible explanation, a mathematical specter lurking in the equations of general relativity. But here's the twist: while the math allows for its existence, no one knows if it's real. It could be a fluke in our measurements, a gap in our theories, or a genuine cosmic threat hiding in plain sight. What makes phantom energy so unsettling isn't just its destructive potential, it's the timeline. Unlike the slow, cold demise of heat death or the fiery collapse of the Big Crunch, the Big Rip could happen relatively quickly on cosmic scales. Some models suggest it might take tens of billions of years, while others hint at a far swifter end. And that uncertainty is what keeps scientists awake at night. If phantom energy is real, and if its strength crosses a critical threshold, the countdown to the universe's final moment could already be ticking away, silent and invisible like a time bomb buried in the fabric of reality itself. The Big Rip isn't just another cosmic doomsday scenario. It's a slow-motion apocalypse that would unfold in terrifying stages, each more destructive than the last. In the beginning, the effects would be almost imperceptible. Galactic clusters, those colossal families of galaxies bound by gravity, would start drifting apart as the space between them stretches faster than gravity can pull them back together. Neighboring galaxies like Andromeda, which is currently on a collision course with our Milky Way, would instead recede into the void, their light stretched into invisibility as the accelerating expansion outpaces the speed of light itself. Over time, even the closest stars would vanish from our night sky, leaving our solar system isolated in an ever-expanding darkness. But the horror wouldn't stop there. As phantom energy's grip tightens, the bonds holding solar systems together would snap. Planets would be yanked away from their stars, their orbits unraveling like thread from a spool. Earth, if it still existed by this point, would drift into the freezing abyss, severed from the sun's warmth. Next, stars themselves would disintegrate, their immense gravity no match for the phantom force tearing space apart from within. And then in the final moments, matter itself would dissolve. Atoms, the fundamental building blocks of everything we know, would be ripped apart as the space between protons and electrons expands faster than the electromagnetic force can hold them together. Even atomic nuclei would splinter, their quarks torn asunder in a last, violent instant. The universe wouldn't just end, it would be erased piece by piece until nothing remained. The key to this nightmare lies in a deceptively simple number. The equation of state, represented by the letter W in cosmology, this ratio compares the pressure of dark energy to its density. For the Big Rip to occur, W must drop below -1, crossing into phantom territory. Current observations suggest dark energy's W is eerily close to this threshold, hovering around -0.95. But close isn't enough. Phantom energy demands a decisive leap into the unknown. If W dips even slightly lower, the universe could be locked onto a one-way path to destruction. The problem, we don't know what drives W to begin with. Is it a constant, or could it evolve over time, inching us closer to the brink without warning? This uncertainty is what makes the Big Rip so unnerving. Unlike other cosmic endings, which play out over near unimaginable timescales, the rip could happen within tens of billions of years, a blink in cosmic terms. Some models even suggest that if phantom energy's influence grows rapidly, the end could come much sooner. And here's the most chilling part, we might not see it coming. The very forces tearing the universe apart would also erase the evidence, stretching light from distant galaxies beyond detection and masking the truth until it's too late. The cosmos could already be on borrowed time, and we'd have no way to know until the fabric of reality itself begins to fray. Dark energy and phantom energy might sound like two sides of the same coin, both mysterious forces driving the universe's expansion. But the difference between them could mean the difference between a slow cosmic drift and an all-out annihilation. Think of dark energy as the steady hand guiding the universe's growth, like a gentle breeze pushing a sailboat across an endless ocean. It's been with us since the dawn of time, subtly accelerating the space between galaxies without tearing them apart. But phantom energy, it's that same breeze turning into a hurricane, growing stronger with every passing moment until nothing can stand in its way. To grasp just how radically these forces differ, look to the tools scientists use to measure them. Supernovae, the brilliant explosions of dying stars, act as cosmic mile markers. By studying how their light stretches as the universe expands, researchers can calculate the rate of acceleration. Then there's the cosmic microwave background, the faint afterglow of the Big Bang, which holds clues about the universe's structure and the forces shaping it. Galaxy clustering adds another piece of the puzzle. The way galaxies clump together reveals how strongly dark energy, or something far more sinister, is pulling them apart. Yet despite all this cutting-edge observation, the data remains frustratingly ambiguous. Dark energy fits neatly into many of our models, its effects consistent with a universe expanding at a predictable pace. But phantom energy lingers at the edges of the data, a ghostly possibility that could upend everything. Some measurements hint at anomalies, tiny deviations in the expected rate of expansion that could suggest phantom energy's influence. But are these just statistical flukes, or the first whispers of a coming catastrophe? The stakes couldn't be higher. If dark energy is all that's at work, the universe faces a slow, cold future where galaxies fade into isolation. But if phantom energy is real, that future becomes a ticking clock. Every observation, every calculation, is a race to answer one terrifying question. Are we reading the universe's final chapter without even realizing it? The line between these two possibilities is razor-thin, and until we cross it or rule it out entirely, the fate of everything hangs in the balance. Humanity's fascination with cosmic endings stretches back, long before telescopes or quantum physics. Ancient civilizations spun myths of worlds consumed by fire, flood, or chaos, like the Norse or Hindu, as if echoing an instinctual understanding that nothing lasts forever. Even early astronomers like Ptolemy, mapping the heavens with naked eyes, sensed a hidden tension in the stars, though they lacked the tools to articulate it. The scientific revolution transformed these whispers into equations. Newton's laws of motion first hinted at a clockwork universe, yet his theories couldn't explain why the night sky didn't collapse under gravity's pull. Centuries later, faced a similar paradox. His general relativity equations predicted an unstable cosmos, one that should either expand or contract, leading him to famously insert a cosmological constant as a fudge factor to keep the universe static. He'd later call this his greatest blunder, unaware how prescient it would become. The real turning point came in the 1920s, when observations shattered the illusion of a steady, eternal universe. Galaxies weren't fixed in place. They were racing away from one another, evidence of space itself stretching. This discovery of cosmic expansion birthed modern cosmology, and with it, urgent new questions. Would gravity eventually reverse the expansion, crushing everything back into a singularity? Or would the universe keep growing indefinitely, fading into darkness? For decades, these were the only two endings scientists considered plausible. Then, in the late 1990s, everything changed. Measurements of distant supernovae revealed something shocking. Expansion wasn't just continuing, it was accelerating. An unknown force, later dubbed dark energy, was overpowering gravity. The cosmos wasn't merely drifting apart, it was being open. Phantom energy emerged from this revelation like a shadowy counterpart to dark energy. The concept was first rigorously explored in the early 2000s by theorists like Robert Caldwell, who saw hints in equations that dark energy might not be as benign as initially thought. If its repulsive power grew stronger over time, it could cross a threshold where space itself lost all cohesion. What makes this idea so provocative isn't just its apocalyptic implications, it's how it inverts centuries of scientific intuition. Newton sought stability, a universe governed by predictable forces. Phantom energy suggests the opposite, a reality where the rules themselves might unravel. Today, as cosmologists scrutinize the faint afterglow of the Big Bang and track galaxies billions of light years away, they're essentially reading the universe's vital signs for clues. Each new dataset, whether from space telescopes like Euclid or ground-based observatories, could tip the scales between dark energy's steady push and phantom energy's runaway destruction. The irony is palpable. After pondering the cosmos's fate, we might finally be closing in on an answer, only to find it's far stranger than any myth or theory predicted. The universe's ultimate destiny could hinge on a number we haven't yet measured with certainty, hiding in the space between equations and the vast, indifferent expanse of the sky. At the core of this cosmic mystery lies a number so deceptively simple, it holds the universe's fate in its digits, the equation of state. Represented by the letter W, this ratio compares the pressure of dark energy to its density, a relationship that dictates how space expands. For most of the universe's history, W hovered around -1, a delicate balance where dark energy's repulsive force countered gravity's pull without spiraling out of control. But phantom energy shatters that equilibrium. To trigger a big rip, W must plunge below -1, crossing into uncharted territory where the rules of physics warp. Here's the paradox. A value below -1 implies that phantom energy's density increases as the universe expands, like a spring that stiffens the more you stretch it. Conventional matter does the opposite. Think of a balloon losing pressure as it inflates. This inversion defies intuition, suggesting phantom energy behaves less like a force and more like a glitch in reality's code. If true, it would mean the universe's expansion isn't just accelerating. It's self-reinforcing, growing stronger until it overpowers every binding force in existence. Measuring such an abstract property might seem impossible, but cosmologists have devised ingenious methods. One key tool is baryon acoustic oscillations, frozen ripples in the distribution of galaxies, relics of sound waves from the early universe. By mapping how these patterns stretch over time, scientists can calculate expansion rates with precision. Another clue comes from weak gravitational lensing, where distant light bends around massive objects, subtly distorting their shapes. The degree of distortion reveals how much space has stretched between us and those far-off galaxies, offering indirect evidence of dark energies, or phantom energies, grip. Yet the most tantalizing data comes from type supernovae, the cosmic lighthouses that first revealed dark energy's existence. These stellar explosions shine with near-identical brightness, allowing astronomers to gauge their distances and track how fast the universe grows between them and us. If phantom energy is at work, supernovae farther away should appear dimmer than expected, their light stretched thinner by an expansion rate spiraling out of control. So far, results are inconclusive, hovering tantalizingly close to the phantom threshold without definitively crossing it. The challenge is compounded by the universe's sheer scale. Even light from the nearest supernova takes millions of years to reach us, meaning we're peering into the past, not the present. Simulations help bridge this gap, using supercomputers to model how phantom energy might alter cosmic structures over billions of years. Some predict galaxy clusters dissolving faster than standard dark energy would allow, while others suggest spacetime might develop microscopic cracks long before the Big Rip's final cataclysm. But simulations are only as good as the assumptions they're built on, and right now, those assumptions are threads in a tapestry we're still weaving. What makes the equation of state so haunting isn't just its mathematical elegance, it's the stakes. A value of -1.01 might seem trivial, but it could lock the universe onto an inescapable path to destruction. The difference between a slow cosmic fade and a violent end hinges on a decimal place. And while today's telescopes push the limits of observation, the ultimate test may lie in the next generation of technology, space observatories like the European Space Agency's Euclid, designed to map billions of galaxies with unprecedented precision. Until then, W remains a cipher, its true value hidden in the dark between the stars. The hunt for phantom energy is like piecing together a cosmic jigsaw puzzle where half the pieces are missing, and the rest might be illusions. Astronomers have no direct snapshot of this elusive force, but they've scoured the universe for subtle fingerprints, sifting through light from dying stars, ancient sound waves frozen in time, and the warped images of distant galaxies. Each clue is fragile, open to interpretation, yet tantalizing enough to keep the search alive. Take type supernovae, the universe's standard candles. These stellar explosions shine with such predictable brightness that scientists use them to measure cosmic distances. By tracking how their light stretches as space expands, researchers can calculate whether the universe's growth is speeding up, and if so, how fast. Some supernovae appear fainter than expected, as if space is stretching more aggressively than dark energy alone can explain. Could this be phantom energy's calling card? Maybe. But interstellar dust, measurement errors, or even unknown supernova quirks could mimic the same effect. The data whispers, but it doesn't shout. Then there are baryon acoustic oscillations, ghostly ripples in the cosmic web. These patterns, imprinted in the early universe by pressure waves, act like a ruler etched into space. By measuring how these ripples stretch over billions of years, scientists can gauge the universe's expansion history. Some studies hint at anomalies, tiny deviations from the expected rate, that align with phantom energy's chaotic influence. But like a faint radio signal buried in static, the evidence is too tentative to confirm anything. Weak gravitational lensing adds another layer of intrigue. When light from distant galaxies bends around massive objects, it distorts their shapes like a funhouse mirror. The degree of distortion reveals how much space has expanded along the light's journey. Some observations suggest the universe's expansion might be accelerating faster than standard dark energy predicts, as if an invisible hand is cranking up the speed. But again, the margin for error is slim. The difference between phantom energy and a statistical fluke could come down to a fraction of a percent in the data. Upcoming missions like the James Space Telescope and the European Space Agency's Euclid could tip the scales. With unprecedented precision, they'll map billions of galaxies, peer deeper into the cosmic microwave background, and scrutinize supernovae across unimaginable distances. These tools might finally spot the smoking gun or rule out phantom energy entirely. But time is a double-edged sword. Every second we spend searching is another second the universe keeps expanding, potentially inching closer to a fate we can't yet see. The irony is profound. We're racing against the very force we're trying to measure, chasing shadows in the dark before the dark swallows us whole. Phantom energy doesn't just threaten the universe. It shakes the very foundations of quantum physics, forcing scientists to confront whether our deepest laws might be flawed. At the heart of this clash is the dominant energy condition, a bedrock principle stating that energy can't flow faster than light or become negative in ways that defy causality. It's a rule woven into the fabric of relativity and quantum theory, ensuring the universe behaves predictably. Yet phantom energy gleefully tramples over it. If this force grows stronger as space expands, as its equations suggest, it could violate this condition, upending our understanding of how energy and gravity interact. Imagine a river that flows faster the wider it gets, defying all logic. That's the paradox phantom energy introduces to the cosmos. This dilemma has split physicists into two camps. One group argues that phantom energy is a mathematical mirage, a quirk of equations that vanishes when scrutinized under the full weight of quantum field theory. They point out that similar anomalies have appeared before, like the ultraviolet catastrophe in early radiation studies, only to dissolve when deeper physics was uncovered. To them, phantom energy is a placeholder for gaps in our knowledge, not a real phenomenon. But others see it as a beacon, hinting at undiscovered layers of reality. Some theorists have proposed radical tweaks to quantum field theory, suggesting that phantom energy could emerge from exotic particles or higher dimensions. These models are speculative, but they share a thrilling premise. The universe might be stranger than our current theories allow. The stakes here are enormous. If phantom energy is real, it wouldn't just doom the cosmos, it would expose cracks in our most trusted frameworks. Quantum mechanics and relativity, the twin pillars of modern physics, have survived a century of tests, yet phantom energy dangles the possibility that they're incomplete or that some hidden interaction waits to be discovered. It's a humbling reminder that for all our progress, the universe still holds cards close to its chest. What makes this debate so electrifying is the data vacuum at its center. Unlike dark matter or black holes, phantom energy leaves no direct trace. Its existence must be inferred from cosmic expansion patterns, a bit like diagnosing a fever by watching someone's shadow grow longer. Until new instruments like the Observatory or next-generation space telescopes deliver sharper measurements, the question remains open. Is phantom energy a fluke, a flaw, or a key to rewriting physics itself? The answer could redefine not just the universe's fate, but our understanding of reality's rules. The universe's birth and death might be more connected than we ever imagined. Cosmic inflation, that split-second explosion of expansion right after the Big Bang, was driven by a mysterious energy field that vanished as abruptly as it appeared. But what if it didn't fully disappear? Some theorists propose that phantom energy could be inflation's distant cousin, a late-stage resurgence of that same primordial force, echoing across billions of years. Picture a pendulum swinging once with incredible force, then barely moving for eons before swinging back with equal violence. If inflation was the first swing, phantom energy might be the return arc, a cosmic symmetry hidden in the equations of time itself. This idea hinges on a peculiar similarity between the two phenomena. During inflation, space expanded faster than light itself, doubling in size countless times in fractions of a second. Phantom energy, if it grows unchecked, could trigger a similar runaway expansion. Only this time, instead of creating the universe, it would dismantle it. The math suggests both events might stem from the same kind of exotic energy field, one that warps spacetime in ways that defy conventional physics. It's as if the universe encoded its own destruction in its birth cries, a secret waiting to be decoded in the faint ripples of the cosmic microwave background. Yet connecting these dots is no easy task. Inflation left behind traces, subtle fluctuations in the density of the early universe that eventually seeded galaxies. Phantom energy, by contrast, leaves no such fingerprints. Its effects are stealthy, cumulative, visible only in the stretching void between galaxies over billions of years. To test this cosmic symmetry, scientists are digging deeper into inflation's relics, searching for anomalies that might hint at a shared mechanism. Some models even suggest that if phantom energy is real, it could produce microscopic spacetime defects, tiny cracks in the fabric of reality that echo the quantum fluctuations of the early universe. The implications are staggering. If inflation and phantom energy are two faces of the same force, it would mean the universe's fate was sealed in its first moments. The same physics that set stars and galaxies in motion could one day tear them apart. But here's the catch. Inflation remains theoretical, its details hotly debated. Without a definitive understanding of how it worked, proving a link to phantom energy is like assembling a puzzle with half the pieces missing. New telescopes probing the cosmic microwave background, or gravitational wave detectors, listening for echoes of the Big Bang, might one day find the missing clues. Until then, this cosmic symmetry remains a haunting possibility, a reminder that the universe's beginning and end might be chapters of the same dark, beautiful story. The vacuum catastrophe is one of the most jarring contradictions in modern physics, a glaring mismatch between theory and reality that makes phantom energy's puzzle seem almost tame. Quantum field theory, our most precise framework for understanding particles and forces, predicts that empty space should buzz with an unimaginable amount of energy. Every cubic centimeter of the vacuum ought to contain enough power to rip apart the fabric of spacetime itself. But when we measure the actual energy density of the cosmos, it's almost zero. A discrepancy so vast it's like comparing the size of a single atom to the entire observable universe. This isn't just a minor oversight, it's a crisis at the heart of physics, and phantom energy might be the twisted solution no one saw coming. Here's the terrifying symmetry. If phantom energy exists, its bizarre properties could help bridge this gap. The vacuum's predicted energy might not be missing. It could be lurking in a form we barely understand, its repulsive force growing stronger as space expands. Imagine a hidden reservoir of energy, undetectable until its effects become catastrophic. As the universe stretches, this energy wouldn't dilute like ordinary matter or radiation. Instead, it would intensify, its density climbing until it dominates everything. In this scenario, the vacuum catastrophe isn't a flaw in our math, it's a countdown. The same energy that could solve one of physics' greatest mysteries might also be the force that tears reality apart. Yet there's a chilling alternative. What if the vacuum catastrophe and phantom energy are both red herrings? Some theorists argue that the mismatch arises because we're applying quantum field theory at cosmic scales where it was never meant to operate. Others suggest undiscovered symmetries or new dimensions might cancel out the vacuum's energy in ways we can't yet calculate. The problem is, every proposed fix either feels contrived or opens up even stranger possibilities. For instance, the multiverse theory suggests our universe is just one bubble among countless others, each with different vacuum energies. Ours improbably tuned to allow galaxies, life, and the very questions we're asking. But this shifts the mystery rather than solving it. The stakes here are existential. If phantom energy resolves the vacuum catastrophe, it would mean the universe is fundamentally unstable, its fate sealed by the same equations that describe its birth. But if we're missing something deeper, a law of physics yet to be discovered, then the cosmos might be far more resilient than we fear. Every new observation, from gravitational wave detectors to precision measurements of the cosmic microwave background, is a vote for one future or the other. The vacuum catastrophe isn't just a puzzle for theorists. It's a mirror held up to our understanding, revealing how much we still don't know about the forces shaping reality. And until we solve it, phantom energy will loom as both a possible answer and an unthinkable price. Phantom energy may be the universe's most dramatic doomsday scenario, but it's far from the only explanation on the table. Enter quintessence, a dynamic cousin to dark energy that could rewrite the cosmic rulebook without the apocalyptic finale. Unlike phantom energy's runaway destruction, quintessence is more like a cosmic thermostat, its strength ebbing and flowing over time. Picture a river that slows or speeds up depending on the season, rather than a flood that never stops rising. This subtle variability could explain the universe's accelerating expansion while dodging the Big Rip's violent endgame. Some models even suggest quintessence might eventually fade, allowing gravity to regain dominance in a distant future where galaxies drift closer instead of farther apart. But quintessence isn't without its own puzzles. To match observations, theorists must fine-tune its properties with near-magical precision, adjusting how it interacts with matter and evolves across billions of years. It's like balancing a pencil on its tip in a hurricane, possible in theory but wildly improbable in practice. And while it avoids phantom energy's cataclysmic extremes, quintessence still leaves a gaping hole in our understanding. What is this mysterious field, and why does it exist? The name itself, borrowed from an ancient Greek term for the elusive fifth element, hints at how little we truly grasp. Then there's the radical camp that sidesteps dark energy entirely. Modified gravity theories like MOND, modified Newtonian dynamics, propose that relativity might need a tweak, that gravity behaves differently on cosmic scales than our equations predict. Instead of invoking an invisible energy tearing space apart, these models suggest we've simply misread the universe's gravitational handwriting. Imagine realizing you've been using the wrong ruler to measure a room. The dimensions didn't change, but your tools led you astray. Supporters point to oddities like galaxy rotation curves, where stars orbit faster than Newton's laws allow, as evidence that gravity's rules aren't as universal as we thought. Yet modified gravity faces its own reckoning. While it excels at explaining small-scale anomalies, it struggles to account for the full scope of cosmic acceleration without resorting to patches that feel just as odd as dark energy. The cosmic microwave background, that snapshot of the infant universe, aligns too neatly with relativity's predictions to discard its framework entirely. It's like trying to fix a watch with a hammer. Some gears might click into place, but others shatter under the force. The most tantalizing possibility, that the truth lies in a hybrid of these ideas. Maybe dark energy and modified gravity aren't rivals, but pieces of a larger puzzle we haven't assembled yet. Some theorists explore scenarios where our universe is a three-dimensional membrane floating in a higher dimensional space, its apparent expansion shaped by unseen forces beyond our perception. Others toy with holographic principles, suggesting gravity's weakness compared to other forces is a cosmic illusion, a shadow cast by deeper laws etched on the universe's boundary. What's striking isn't just the diversity of theories, but what they share, a humbling acknowledgement that our cosmic map still has blank spaces. Phantom energy's visceral drama captures headlines, but the quieter alternatives remind us that the universe's secrets rarely surrender to simple explanations. Every anomaly in the data, every tension between theory and observation, is a breadcrumb trail, one that could lead to a paradigm shift or a dead end. Until new telescopes or particle accelerators unveil the next clue, the debate rages on. Is the cosmos a ticking time bomb, or are we just beginning to read its true story? Black holes are often seen as the ultimate cosmic survivors, entities so dense that not even light can escape their grasp. They devour stars, warp spacetime, and persist for unimaginable eons, outlasting galaxies and even the slow fade of heat death. But phantom energy doesn't play by those rules. In the face of the Big Rip, even these gravitational behemoths would meet their match. As space stretches faster and faster, phantom energy's repulsive force would eventually overpower the very fabric holding black holes together. Picture a mountain crumbling not from erosion, but because the ground beneath it is being yanked apart faster than gravity can compensate. The universe's most indestructible objects would unravel in a final, violent act of dissolution. This isn't just a dramatic end for black holes, it's a crisis for physics itself. This theory of general relativity predicts that black holes are eternal, their singularities hidden behind event horizons that nothing can breach. But phantom energy throws a wrench into that certainty. If space itself tears apart the event horizon, the point of no return would be shredded before the singularity inside could vanish. This paradox forces scientists to confront a haunting possibility. Our understanding of black holes, and perhaps gravity itself, might be incomplete. Some theorists suggest that phantom energy's extreme conditions could expose quantum effects normally hidden deep within black holes, revealing secrets about how gravity and quantum mechanics intertwine. The implications ripple even further. Black holes aren't just cosmic vacuum cleaners, they're thought to play a key role in the universe's structure and evolution. Their mergers create gravitational waves, their jets shape galaxies, and their eventual evaporation via Hawking radiation could be the last flicker of activity in a dying cosmos. But the Big Rip wouldn't grant them the dignity of slow decay. Instead, they'd be ripped apart mid-existence, their secrets scattered into a void where even spacetime no longer holds meaning. This raises a chilling question. If the universe's most resilient structures are fragile in the face of phantom energy, what does that say about the nature of reality itself? Some physicists speculate that the destruction of black holes might be the universe's final lesson. As phantom energy tears them open, it could unleash phenomena we've never witnessed. quantum gravity effects, hidden dimensions, or even new states of matter. It's like cracking open a cosmic safe only to find the contents redefine the very concept of value. Others argue that the Big Rip's violence would leave no time for observation or understanding. The end would come too quickly, erasing not just matter but the very framework needed to make sense of it. The fate of black holes under phantom energy is more than a scientific curiosity. It's a litmus test for our theories. If relativity falters in the face of the Big Rip, it could mean we're missing a deeper layer of physics, one that only reveals itself under the most extreme conditions. Or it could mean that the universe's final moments are as inscrutable as its first. Either way, the death of black holes wouldn't just mark the end of objects. It would mark the end of the rules we've used to explain them. And in that final cataclysm, we might find the answers we've been searching for or lose them forever. Time has always moved forward in our universe, an unbreakable rule etched into the fabric of reality. From the moment a cup shatters on the floor to the slow death of stars, entropy, the universe's tendency toward disorder pushes everything relentlessly toward chaos. But phantom energy doesn't just threaten to tear apart galaxies, it could rewrite this fundamental law. In a Big Rip scenario, the expansion of space doesn't just outpace gravity, it could outrun entropy itself. Imagine a river flowing so fast that the water never has time to ripple. The universe's chaotic dance of particles, the very engine of time's arrow, would stall as space stretches faster than disorder can spread. The result: a cosmos where the concept of before and after dissolves into silence. This isn't just a tweak to physics, it's a complete unraveling of cause and effect. Normally, entropy gives time its direction. We remember the past but not the future because entropy was lower then, creating a gradient that shapes our experience of reality. But if phantom energy accelerates expansion to the point where entropy can't keep up, that gradient flattens. The universe would become a static, featureless void where nothing changes, nothing decays, and nothing evolves. Time wouldn't just slow down, it would cease to have any meaning at all. The very idea of the end would become meaningless because there'd be no progression toward it, just an infinite, frozen instant stretched across the carcass of space-time. Some theorists argue this scenario might not just erase time, it could distort the laws of physics entirely. In extreme conditions, phantom energy's repulsive force might overpower not just gravity but the fundamental interactions that hold atoms together. Quantum fields, the invisible scaffolding of reality, could fracture under the strain. The constants we rely on, the speed of light, the strength of electromagnetism, might not be so constant anymore. It's like watching the rules of chess change mid-game, with pieces suddenly moving in ways that defy logic. The universe wouldn't just end, it would forget how to be a universe at all. Yet there's a haunting counterpoint. What if time's arrow isn't truly universal? Cosmologists have long debated whether entropy must always increase in every corner of reality. Some models of quantum gravity suggest that in highly curved or extreme environments, entropy might behave unpredictably, even temporarily decreasing. If true, phantom energy's distortion of spacetime could create pockets where time flows backward or splinters into fragments. Picture a film reel burning in reverse while the rest plays normally, a patchwork of moments with no coherent narrative. The deeper we dig, the stranger the implications become. If phantom energy can disrupt time's arrow, it challenges not just our models of the cosmos, but the bedrock of human experience. Our memories, our history, even our sense of self rely on time's steady march. A universe where that march falters isn't just inhospitable, it's incomprehensible. And that's the true terror of phantom energy. It doesn't just threaten to destroy the universe, it threatens to make it unrecognizable. If phantom energy tears our universe apart, what happens to the countless others that might exist beyond it? According to multiverse theory, our cosmos could be just one bubble in an infinite foam of realities, each with its own unique laws of physics. Some of these universes might have dark energy too weak to trigger a big rip, or none at all, stable cosmic islands untouched by the unraveling that dooms ours. Others could harbor even more volatile forms of phantom energy, their destruction arriving faster, slower, or in ways we can't yet imagine. The terrifying possibility is just that our universe is fragile, but that it might be one of many caught in a cycle of creation and annihilation, like waves rising and collapsing on an endless shore. This raises a haunting question. Is phantom energy a universal executioner or just a local disaster? If the multiverse is real, the answer could depend on something as simple as a number, the equation of state W, that critical ratio determining whether dark energy remains benign or turns predatory. In some universes, W might never dip below -1, sparing them from the big rip's violence. In others, it could plummet far lower, triggering collapses more extreme than anything we've theorized. The randomness of these values suggests a chilling lottery where universes live or die by the luck of their initial conditions. Our cosmic neighborhood might not be special, just unlucky. Yet there's a twist. If phantom energy is tied to the vacuum of space itself, as some theories suggest, it could behave differently in other realities. Imagine universes where the vacuum's energy is negative instead of positive, creating a crushing pull rather than a repulsive push. In those worlds, the end might come not as a rip, but as a crunch, a catastrophic collapse inward. Others might oscillate between expansion and contraction, their phantom energy waxing and waning like a cosmic heartbeat. The multiverse wouldn't just offer escape routes from destruction, it would showcase every possible flavor of apocalypse. The most tantalizing clue lies in the boundaries between these universes. If they're embedded in a higher dimensional space, like bubbles floating in an unseen ocean, phantom energy's effects might ripple beyond our own bubble, leaving faint imprints on neighboring realities. Some models suggest these ripples could manifest as anomalies in the cosmic microwave background, subtle warps in spacetime that hint at something beyond our horizon. Others propose that colliding universes might leave scars in the distribution of galaxies, patterns that only make sense if another cosmos once brushed against ours. Phantom energy wouldn't just be a death sentence, it could be a messenger, carrying news of realities we'll never see. But here's the ultimate irony. Even if the multiverse teems with life and variety, we may never know for sure. The same force that could reveal other universes, phantom energy's relentless expansion, would also ensure we're forever cut off from them. As space stretches faster than light can travel, every other reality would vanish beyond an unreachable horizon, leaving us alone with our doom. The multiverse might be infinite, but our window to it is closing. And that's the real tragedy of phantom energy, not just the end it brings, but the answers it takes with it. The idea that the universe could one day tear itself apart doesn't just challenge our scientific models, it shakes the very foundation of how we see ourselves. If phantom energy is real and the big rip inevitable, what does that say about the purpose of human existence? Are we just temporary flickers in a cosmic story hurtling toward an abrupt and violent conclusion? Philosophers have wrestled with these questions for centuries, but phantom energy gives them a terrifying new urgency. Some argue that an impermanent universe strips life of meaning. If everything, every galaxy, every planet, every thought and memory will one day be erased, then what's the point of striving, creating, or even caring? This view, known as cosmic nihilism, suggests that in the face of ultimate destruction, all human achievement is just built before the tide rolls in. But others push back fiercely. They see the universe's fragility not as a reason to despair, but as a call to action. If our time is limited, they argue, then every moment becomes more precious, not less. The knowledge that the cosmos could end not with a whimper but a rip might be the very thing that galvanizes us to explore farther, dig deeper, and leave our mark while we still can. This tension between despair and determination isn't just theoretical, it's playing out in real time among the scientists studying phantom energy. Some admit that the possibility of a big rip keeps them up at night, not because of the physics, but because of what it implies about our place in the grand scheme. Others channel that unease into curiosity, treating the mystery as the ultimate puzzle to solve. The late cosmologist Stephen Hawking once said that even if the universe is doomed, understanding why gives our brief existence a kind of nobility. In his words, we are just an advanced breed of monkeys on a minor planet of a very average star, but we can understand the universe. That makes us something very special. And then there's the most haunting question of all. Why is there something rather than nothing? Phantom energy doesn't just threaten the universe's future, it forces us to confront the mystery of its origins. If the same force that might destroy everything also played a role in creation, as some theories suggest, then existence itself becomes a loop of beginnings and endings, with no ultimate explanation. Theologians and physicists alike have circled this question but phantom energy adds a grim twist. The answer might be obliterated before we ever find it. Yet here's the paradox. The very act of asking these questions defies the void. As long as we're here to ponder the universe's fate, we're asserting a kind of meaning against the darkness. Whether phantom energy is real or not, the debate it sparks reveals something profound about humanity. We're the universe's way of understanding itself, even if that understanding is fleeting. And in that role, we might find a purpose no big rip can erase. Detecting phantom energy is like trying to spot a shadow in a pitch-black room when we can barely see the objects casting it. Our current telescopes and sensors, as advanced as they are, were never designed to hunt something so elusive. Dark energy itself, the far tamer cousin of phantom energy, took decades to confirm, and even now, we've only glimpsed its effects indirectly. Phantom energy's extreme nature makes it exponentially harder to pin down. If it exists, its signal is buried under cosmic noise, masked by the very expansion it drives. The universe might be screaming its demise at us, but our instruments aren't yet sensitive enough to hear. That's where next-generation observatories come in. The telescope, set to begin its survey of the sky in the next few years, will map billions of galaxies with unprecedented precision, tracking how their distributions change over time. If phantom energy is subtly tweaking the rate of cosmic expansion, could spot the anomalies, tiny deviations in galaxy clustering or supernova brightness that today's telescopes miss. Then there's the Square Kilometer Array, a sprawling radio telescope network that will listen for the faint echoes of the early universe. By measuring how cosmic structures warp and stretch across billions of light years, it might catch phantom energy's fingerprints in the way space itself distorts. Yet even these colossal projects might not be enough. Phantom energy's most damning evidence could lie beyond our observational horizon, literally. If the universe's expansion is already accelerating faster than light in some regions, their light will never reach us, locking away critical data forever. Some scientists propose radical workarounds, like sending probes beyond our solar system to measure cosmic expansion locally. Imagine a spacecraft equipped with ultra-precise lasers, firing pulses across the void to track how space stretches between here and there. But the distances involved are staggering. Even at the speed of light, such a mission would take to gather meaningful data, assuming humanity lasts that long. The real hurdle isn't just technological, it's time. Phantom energy's threat is a slow burn, unfolding over timescales that dwarf human civilization. By the time we gather definitive proof, it might be too late to matter. That's why researchers are racing to develop indirect methods, like hunting for quantum fluctuations in the vacuum of space or searching for microscopic cracks in spacetime that could signal phantom energy's presence. Others are turning to simulations, using supercomputers to model universes with varying W values, hoping to spot patterns that match our observations. The irony is crushing. We might be living in the one era where phantom energy's existence is both detectable and relevant, after enough time has passed for its effects to emerge, but before it erases all traces of itself. Future civilizations, if they exist, could be left staring at an empty sky, their telescopes peering into a void where galaxies once shone. The answers we seek might be slipping through our fingers even now, lost in the expanding dark. Whether humanity solves this riddle depends not just on our tools, but on our willingness to confront a truth that could rewrite our destiny. String theory has long been the wild frontier of physics, a realm where the usual rules bend and break in ways that defy common sense. At its core, it proposes that the fundamental building blocks of the universe aren't point-like particles but tiny, vibrating strings, with their resonance patterns determining everything from quarks to gravity. But when it comes to phantom energy, string theory takes this strangeness to new heights. Some models suggest that the extra dimensions it predicts, those hidden, curled-up realms beyond our four familiar ones, could be the key to understanding why phantom energy behaves so destructively. Imagine a force leaking into our universe from these higher dimensions, growing stronger as space expands, like water seeping through cracks in a dam. One tantalizing idea is that phantom energy might be tied to brains, membranes of reality floating in higher dimensional space. In certain string theory scenarios, our universe could be a three-dimensional brain colliding or interacting with others, creating ripples that manifest as dark energy. If those interactions grow unstable over time, they might produce the runaway expansion characteristic of phantom energy. It's a bit like two sheets of paper fluttering in a breeze. When they brush against each other, the friction could warp our cosmic landscape in ways we're only beginning to model. Yet string theory's potential answers come with a catch. They're almost impossible to test. The energy scales involved in probing extra dimensions or vibrating strings are far beyond what our particle colliders can reach. Even the Large Hadron Collider, which discovered the boson, operates at energies trillions of times too weak to glimpse these phenomena. Some theorists propose indirect signatures, like subtle anomalies in gravitational waves or distortions in the cosmic microwave background. Others hope that black holes, nature's extreme laboratories, might reveal clues, as their singularities could fray into strings under the right conditions. But so far, these remain speculative hunches, not hard evidence. The debate among physicists is fierce. Critics argue that string theory's connection to phantom energy is little more than mathematical storytelling, an elegant narrative with no grounding in observable reality. They point out that after decades of work, string theory still hasn't produced a single testable prediction about our universe, let alone its demise. Supporters counter that the same was once true of black holes and gravitational waves, ideas that seemed purely theoretical until technology caught up. The difference, of course, is that phantom energy's clock might already be ticking. What makes this intersection so electrifying isn't just the science, it's the philosophical stakes. If string theory does explain phantom energy, it would mean the universe's fate is written in dimensions we can't see, governed by rules we can't yet fathom. But if it's a dead end, we're back to square one, staring into the abyss with no framework left to guide us. The strings may be silent for now, but their vibrations could hold the secret to whether our cosmic story ends with a whisper or a scream. The cosmic microwave background is more than just a relic of the Big Bang. It's a time capsule, carrying whispers from the universe's infancy that could reveal phantom energy's hidden influence. This faint glow, bathing every corner of space, is riddled with microscopic temperature variations, imprints of density fluctuations from when the cosmos was just 380,000 years old. These patterns aren't random. They're a blueprint, encoding how gravity, dark energy, and possibly phantom energy have sculpted cosmic structures over billions of years. When the European Space Agency's satellite mapped these fluctuations with exquisite precision, it wasn't just capturing a snapshot of the past, it was holding up a mirror to the universe's fate. The key lies in how phantom energy would warp these primordial ripples. Normally, dark energy's steady push leaves a predictable signature. Galaxy clusters form at a certain rate, and the CMB's fluctuations follow a specific statistical pattern. But phantom energy, with its escalating strength, would distort this picture. Imagine stretching a photograph unevenly. Some features blur while others distort in unexpected ways. Phantom energy's grip on spacetime could leave similar warps in the CMB's texture. Subtle anomalies where the distribution of hot and cold spots deviates from standard dark energy's predictions. This data already holds tantalizing hints. Certain large-scale fluctuations appear slightly weaker than our models anticipate, as if something, perhaps phantom energy, has been suppressing the growth of cosmic structures over time. Other anomalies, like the infamous cold spot, a vast region of unexpectedly low temperature, could be phantom energy's fingerprints, though alternative explanations exist. The challenge is separating signal from noise. The CMB is a palimpsest, layered with effects from interstellar dust, galactic magnetic fields, and even quirks of our own solar system. Teasing out phantom energy's contribution is like listening for a single instrument in a symphony playing at the edge of hearing. Next-generation experiments like the Observatory and CMB-S4 aim to cut through this noise. With detectors 10 times more sensitive than this, they'll scan the CMB in unprecedented detail, hunting for phantom energy's telltale distortions. Some theories suggest these experiments might spot ghostly voids regions where phantom energy has thinned matter's distribution more aggressively than standard expansion allows. Others predict faint, swirling patterns in the CMB's polarization, evidence of gravitational waves amplified by phantom energy's violent push. But here's the cosmic irony. The very force we're trying to detect might be erasing the evidence we need. If phantom energy is real, its accelerating expansion could eventually stretch the CMB's light beyond it into oblivion. We might be living in a unique window, late enough to see the CMB clearly, but early enough to catch phantom energy's first whispers before they fade forever. The universe's oldest light isn't just a glimpse backward, it's a countdown clock, ticking toward either revelation or oblivion. And with every new observation, we're one step closer to knowing which it will be. Simulating the Big Rip is like pressing fast forward on the universe's demise, a digital crystal ball where supercomputers render the unthinkable in vivid detail. These aren't just abstract equations scrolling across a screen, they're dynamic portraits of annihilation. Picture trillions of lines of code translating phantom energy's relentless push into galaxies wrenched apart, their stars scattering like dust in a hurricane. Spacetime itself stretches until it fractures, pixel by pixel, in simulations so precise they border on prophecy. Scientists at institutions like the Flatiron Institute and CERN run these models on machines capable of quadrillions of calculations per second. Yet the results feel less like data and more like a documentary from the end of time. But these simulations come with a catch. They're only as good as the assumptions baked into them. Take the equation of state, W, that critical number determining phantom energy's ferocity. In most models, it's set just below -1, the threshold for a big rip. But what if it fluctuates? Or worse, what if phantom energy interacts with dark matter in ways we haven't accounted for? Running a simulation requires simplifying reality, trimming the universe's infinite complexity into something a computer can digest. It's like predicting a hurricane's path while ignoring the ocean's currents. The results might look convincing, but they could be missing the storm entirely. Then there's the chaos factor. The universe isn't a static backdrop. It's a seething web of quantum fluctuations, black hole mergers, and unseen forces. Even the most advanced simulations struggle to capture how phantom energy might warp under these extremes. Some models suggest space-time could develop microscopic cracks long before the Big Rip's climax, like ice fissuring under pressure. Others hint that phantom energy might cluster unevenly, creating voids where matter collapses faster than predicted. These nuances aren't just academic. They could mean the difference between a universe that unravels in 50 billion years and one that holds on for 100. The most haunting limitation: simulations can't account for what we don't know. If string theory's extra dimensions or undiscovered particles alter phantom energy's behavior, today's models wouldn't have a clue. It's like watching a shadow puppet show and mistaking the silhouettes for the real thing. Yet despite these uncertainties, simulations remain our best window into the abyss. They've already revealed one unsettling truth. If phantom energy is real, its destruction wouldn't be a distant, theoretical threat. It would be a countdown etched into the fabric of reality, ticking away whether we're ready or not. The line between simulation and prophecy blurs with every iteration. As supercomputers grow more powerful, they inch closer to replicating the universe's true complexity, or at least our current understanding of it. But that's the paradox. The more accurate the simulation, the harder it becomes to distinguish from reality. We might one day reach a point where the only way to prove phantom energy wrong is to survive its predicted deadline. Until then, these digital doomsdays stand as both a warning and a challenge, urging us to look deeper, question harder, and perhaps find a flaw in the universe's grim itinerary before it's too late. Phantom energy poses a uniquely unsettling ethical question. Should humanity invest time and resources into studying a doomsday scenario that might not unfold for tens of billions of years? On one hand, the very thought seems absurd when our planet faces immediate crises like climate change, biodiversity loss, and resource scarcity. Every dollar spent peering into the cosmos for signs of phantom energy is a dollar not spent mitigating wildfires, rising sea levels, or food insecurity. Critics argue this is the ultimate in misplaced priorities, a luxury of curiosity when survival demands pragmatism. Why obsess over the universe's distant demise when our own civilization's fragility demands urgent attention? Yet this perspective overlooks a fundamental truth about human nature. We are explorers by design. From the first civilizations charting the stars to the modern era probing quantum realms, the pursuit of knowledge has always coexisted with the struggle for survival. Understanding phantom energy isn't just about predicting doom, it's about unraveling the fabric of reality itself. Dark energy's discovery revolutionized cosmology, proving that the universe's expansion accelerates against all expectations. Phantom energy could be the next paradigm shift, revealing forces or dimensions we've yet to imagine. Dismissing it as irrelevant ignores history's lesson. Today's abstract research often becomes tomorrow's foundational technology. The same quantum mechanics once deemed esoteric now powers our smartphones and medical imaging. The debate also hinges on how we define urgency. Climate change operates on a timescale of decades, phantom energy on eons. But unlike environmental collapse, which we can actively mitigate, the Big Rip offers no recourse. If phantom energy is real and its equation of state dips below -1, no future technology could stop it. Knowing this sooner rather than later could redefine humanity's long-term trajectory, perhaps motivating interstellar expansion as a survival strategy or redirecting scientific focus toward physics-breaking breakthroughs. Underlying this tension is a deeper philosophical rift. Is science merely a tool for solving practical problems, or is it a cultural endeavor, a way to make meaning of our place in the cosmos? For some, phantom energy research exemplifies the latter, a testament to our need to confront existence's biggest questions, regardless of immediate utility. Others see it as intellectual indulgence in a world burning with inequity. The balance between these views isn't just about funding allocations. It's about what kind of civilization we aspire to be. Perhaps the most compelling argument for studying phantom energy lies in its unpredictability. Cosmic timelines are estimates, not guarantees. If phantom energy's strength escalates faster than models predict, its effects could manifest sooner, not in billions of years, but millions or even less. The universe owes us no warning. By the time the evidence becomes undeniable, it might be too late to adapt. In that light, investigating phantom energy isn't a distraction. It's the ultimate contingency plan. The ethical dilemma mirrors humanity's eternal balancing act, tending the fire at our feet while daring to study the stars. Both endeavors define us. Ignoring either risks losing something essential, whether it's our home or our wonder. Phantom energy challenges us to hold both truths at once, to care deeply about the present without surrendering the future's mysteries to the dark. Phantom energy's grip on our collective imagination stretches far beyond the pages of scientific journals. It's seeped into the stories we tell, the art we create, and the music that scores our lives. Take Hollywood's obsession with cosmic cataclysms. Films like Interstellar and Melancholia don't just entertain. They let us rehearse the end of everything in the safety of a darkened theater. These narratives often borrow the language of phantom energy, depicting galaxies ripped apart or time itself unraveling, even if they never name the force behind it. There's something primal in these visions, a way to confront the unthinkable without flinching. It's no accident that some of the most haunting scenes in sci-fi involve characters staring into the abyss, not with despair, but with a strange, almost reverent awe. This fascination isn't confined to blockbusters. Avant-garde composers have translated phantom energy's eerie crescendo into sound, experimental symphonies where notes stretch and distort, mimicking the universe's accelerating expansion. Visual artists, too, chase the same dread and wonder, painting canvases where galaxies fracture like glass or sculpting installations that seem to pull apart at invisible seams. These works don't just illustrate a theory, they give it emotional weight, turning abstract equations into something visceral. When a poet writes about stars unspooling into the dark, they're not citing peer-reviewed studies. They're channeling the same existential tremor that haunts cosmologists. Why does this particular flavor of doom resonate so deeply? Psychologists suggest apocalyptic art serves as a pressure valve, letting us grapple with mortality on a scale that dwarfs individual fears. If the whole universe is fragile, our own fleeting lives suddenly feel less lonely in their impermanence. But there's another, brighter side to this obsession. Phantom energy's cultural footprint also reveals our stubborn defiance. Every painting, song, or story about cosmic annihilation is, in its way, an act of rebellion, a refusal to let the universe's indifference go unchallenged. Even as we stare into the void, we're compelled to leave something behind, whether it's a film, a melody, or an equation scrawled on a chalkboard. The irony is delicious. Phantom energy, a force that could erase all traces of existence, has instead inspired a flood of creativity. It's as if humanity, faced with the prospect of ultimate oblivion, responds by building monuments of thought and beauty, shouting into the dark, "We were here." Whether these works outlast the cosmos is beside the point. What matters is that we made them at all, a testament to the strange, stubborn alchemy that turns terror into art and science into song. Long before telescopes peered into the void, sacred texts spoke of cosmic endings. Floods of fire, heavens rolled up like scrolls, worlds dissolved into divine light. These ancient visions now find an eerie echo in phantom energy's Big Rip, where the universe shreds itself apart. For some believers, the parallel is uncanny. The Book of Revelation describes stars falling like figs from a tree, while Hindu scriptures warn of the dissolution where all matter disintegrates back into the infinite. Could these prophecies have glimpsed, through metaphor, the same cataclysm our equations now predict? The intersection of scripture and science sparks heated debate. Evangelical circles sometimes frame phantom energy as validation of biblical apocalypse, a scientific mechanism for God's final judgment. Meanwhile, Buddhist scholars might interpret the Big Rip as the ultimate manifestation of impermanence, a universe fulfilling its nature by returning to emptiness. Yet this convergence isn't universal. Many religious traditions reject the notion that cosmic doom carries moral weight. In Taoist thought, the universe's end would simply reflect the balance of yin and yang, neither good nor evil but inevitable. Similarly, secular scientists bristle at the idea of phantom energy as anything but physics, a mathematical possibility stripped of divine intent. The tension here isn't just about interpretation, it's about authority. Who gets to narrate the universe's final act? Priests with their revelations or physicists with their telescopes? The friction between these worldviews reveals a deeper irony. Science and spirituality both seek to explain existence, yet their methods couldn't be more different. One relies on peer-reviewed data, the other on transcendent experience. Phantom energy forces them into rare dialogue because it confronts us with an ending so absolute it transcends disciplinary boundaries. Jesuit astronomer Brother Guy, who studies meteorites by day and prays by night, embodies this bridge. He argues that science reveals how the universe might end, while faith explores why it matters, not as competing truths but as complementary lenses. Perhaps the most profound question is whether phantom energy aligns with prophecy, but how humanity responds to the possibility of oblivion. Do we see it as a call to repentance, a test of resilience, or simply a cold fact to be studied? The answers say less about the universe's fate than our own capacity to find meaning in the face of the infinite. Whether etched on parchment or in supercomputer simulations, our stories of the end reveal one universal truth. We are creatures who cannot look away from the abyss, even as it gazes back. If phantom energy dooms our universe to a big rip, could any civilization, no matter how advanced, find a way to survive? The question forces us to stretch our imagination beyond known physics. Some theorists suggest engineering on a scale we can barely fathom, like constructing spheres not just to harness starlight, but to warp spacetime itself. Picture a species so advanced they've woven protective bubbles around their worlds, pockets of reality where phantom energy's grip is temporarily held at bay. Others speculate about harnessing black holes as cosmic anchors, using their immense gravity to counteract the expansion tearing everything else apart. These aren't just wild fantasies, they're desperate blueprints for existence in a universe that's actively trying to erase itself. Yet the obstacles are staggering. Phantom energy isn't just pulling galaxies apart, it's unraveling the very fabric of physical laws. No known material could withstand the forces at play once space begins stretching faster than light. Even if a civilization could build structures to survive the initial phases, the endgame is absolute. Atoms themselves disintegrating, leaving no substrate for life or technology. Some scientists argue that survival would require transcending matter entirely, uploading consciousness into quantum fields or higher dimensions untouched by the rip. It's a haunting thought that intelligence might only persist as ripples in an otherwise dead cosmos, echoing long after the stars have blinked out. This speculation isn't just about humanity's future. If other civilizations exist, they'd face the same existential countdown. Would they see the signs earlier to prepare? Or would the universe's acceleration blind them until it was too late? The search for extraterrestrial intelligence takes on new urgency here. A species that cracked interstellar travel might have already fled to younger universes through theoretical wormholes, leaving behind artifacts or signals as cosmic breadcrumbs. Alternatively, the silence of the cosmos could be a grim answer, proof that no one, no matter how advanced, defeats entropy's final victory. What makes this more than a thought experiment is the timeline. If phantom energies' effects escalate exponentially, civilizations might have mere between detection and doom, a blink in cosmic terms. Imagine a society that discovers the rip is inevitable, yet lacks the technology to escape. Their final acts could be monuments, messages etched into neutron stars or gravitational waves, screaming into the void that they existed. Or perhaps they'd turn inward, embracing digital utopias to savor every remaining second before the lights go out. The chilling truth is this: if the Big Rip is real, resilience might not mean survival, it could mean legacy. Whether through art, science, or screams against the dark, the mark we leave could be our only defiance against a universe determined to forget us. And that raises one last, unanswerable question. If others faced this same ending before us, would we even recognize their farewell? The silence of the cosmos has haunted scientists for decades, a mystery known as the Fermi paradox. If the universe is so vast and ancient, why haven't we found any trace of other civilizations? Phantom energy might hold the grim answer. Imagine a universe where intelligent life emerges only in its final chapters, just as the fabric of reality begins to fray. Civilizations could blossom, reach for the stars, and then, before they can signal their neighbors, be torn apart by the accelerating expansion of space. The cosmic window for communication might be brutally short, leaving civilizations like ours to wonder if we're alone, not because life is rare, but because the universe is in too much of a hurry to let anyone say hello. This idea flips the Fermi paradox on its head. Instead of asking why aliens haven't visited us, we might be asking why we can't hear their final cries. Advanced civilizations, if they existed, could have faced the Big Rip long before we evolved, their signals stretched into oblivion by phantom energy's relentless push. Even if they built galaxy-spanning megastructures or beamed messages across the void, the expanding universe would have their transmissions into silence, like whispers lost in a hurricane. The eerie quiet of the cosmos might not be a sign of absence, just terrible timing. But there's a darker twist. If phantom energy's escalation is inevitable, then every civilization, no matter how advanced, is racing against an existential clock. The sheer scale of cosmic time means that civilizations could rise and fall like fireflies in the night, never overlapping long enough to connect. We might be living in the universe's last era where communication is even possible, a fleeting moment before the void swallows all voices. The Great Filter, the hypothetical barrier preventing life from reaching interstellar scales, might not be a cosmic obstacle course at all. It could simply be time running out. Yet this isn't the only possibility. Some theorists argue that if civilizations knew their doom was certain, they might funnel their resources into one desperate gamble, escaping the universe entirely. Wormholes, higher dimensions, or even birthing new baby universes in labs, these aren't just sci-fi tropes, but theoretical last-ditch efforts to outrun annihilation. If any civilization succeeded, their absence wouldn't be a sign of failure, but of transcendence. The silence we perceive might not be emptiness, but the aftermath of a galactic evacuation. The chilling beauty of this idea is that it reframes our loneliness. The universe isn't empty because life is impossible, it's empty because life is ephemeral. Phantom energy doesn't just threaten our future, it might explain our past, revealing why the cosmos feels like a graveyard of missed connections. And if that's true, then every signal we send, every telescope we point at the stars, isn't just a search for companionship. It's a countdown, a test of whether we're the universe's last hope or its final witness. Phantom energy doesn't just stretch space, it could warp time itself, twisting the universe's clock into a funhouse mirror where seconds tick unevenly across the cosmos. Picture two galaxies drifting apart as expansion accelerates. From our vantage point, time in that distant galaxy would appear to slow down, a relativistic effect called time dilation. The light reaching us from those stars wouldn't just be, it would carry echoes of a reality where time flows differently, like a film played at half speed. This isn't science fiction. It's a direct consequence of theory of general relativity, cranked to nightmarish extremes by phantom energy's grip. The implications are dizzying. If time drags in some regions of the universe while racing ahead in others, our observations become a hall of mirrors. Distant supernovae, used to measure cosmic expansion, might appear fainter not because space is stretching faster, but because time itself is stretching their light's journey. Galaxy clusters could seem more dispersed than they truly are, their structures frozen in observational slow motion. Phantom energy's fingerprints would be smudged across the data, disguised by the very distortions it creates. It's like trying to diagnose a storm by watching raindrops fall through a prism. The deeper we look, the more reality fractures. This temporal chaos raises an unsettling question. How much of what we know about the universe is an illusion? The cosmic microwave background, that snapshot of the infant cosmos, might carry phantom energy's temporal warps like shadows on a cave wall. Even the constant, the benchmark for cosmic expansion, could be a mirage if time dilation skews our measurements. Some theorists suggest that phantom energy's time-warping effects might already be hiding in plain sight, masquerading as statistical noise in our telescope's data. The universe's clock isn't just ticking, it's stuttering, and we're only hearing half the beats. Yet there's a cruel irony here. The same relativistic effects that obscure phantom energy might also be our only hope of detecting it. If time dilation is extreme enough, it could leave subtle scars in the way galaxies cluster or how gravitational waves propagate. Future observatories, like the Laser Interferometer Space Antenna, might catch these anomalies, ripples in spacetime that don't quite match predictions. Other clues could lurk in the decay rates of radioactive particles in distant quasars, their half-lives stretched or compressed by phantom energy's temporal tug-of-war. The universe's clock is broken, but the cracks could point us toward the truth. What makes this so unnerving is the scale of the distortion. Time dilation isn't just a local quirk, it's a cosmic hall of mirrors where every observer sees a different now. A civilization in a phantom energy-ravaged region might experience, while we blink, their final signals reaching us as slowed-down whispers long after their world has ended. The very concept of a shared present dissolves, leaving us with a patchwork of realities, each out of sync. Phantom energy doesn't just threaten to tear space apart. It could fracture time into a million shards, leaving us to piece together the universe's fate from the fragments. The deeper we dig, the clearer it becomes. Reality under phantom energy's influence isn't just stranger than we imagine, it's stranger than we can imagine. Time, the one constant we thought we could rely on, becomes fluid, unreliable. Our telescopes might be showing us a funhouse reflection of the cosmos, where distance and duration blur into a single, inscrutable riddle. And somewhere in that distortion lies the answer to whether phantom energy is real, or if we're chasing shadows cast by a universe that's already slipping through our fingers. Gravitational waves, those faint ripples in the fabric of spacetime, aren't just cosmic messengers delivering news of black hole collisions. They could also be phantom energy's most reluctant. Every time two massive objects like neutron stars or black holes spiral into each other, they send shockwaves through the universe, warping spacetime like a stone dropped in a pond. These waves travel billions of light years, carrying secrets about the cosmos's expansion. If phantom energy is really out there, stretching space faster and faster, it should leave its mark on these ripples, subtly altering their journey in ways that could betray its presence. The key lies in how gravitational waves interact with the universe's expansion. Normally, as space stretches, light from distant objects gets its wavelengths pulled longer, like a slinky stretch to its limit. Gravitational waves should behave similarly, but with a crucial twist. Their propagation could reveal whether expansion is smooth and steady or accelerating toward phantom energy's runaway extremes. Imagine shouting across a canyon as the walls slowly move apart. At first, your voice echoes clearly, but if the gap suddenly widens at an ever-increasing rate, the sound distorts, becoming fainter and more fragmented. Phantom energy would do the same to gravitational waves, imprinting its signature in their fading echoes. Current detectors like LIGO and Virgo aren't yet sensitive enough to spot these subtle distortions. They're like listening for a whisper in a hurricane, brilliant at catching the thunder of black hole mergers, but blind to the quieter effects of phantom energy's grip. But the next generation of observatories, like the Laser Interferometer Space Antenna LISA, could change everything. Slated to launch in the next decade, LISA will float in space, free from Earth's seismic noise, with lasers precise enough to detect gravitational waves from supermassive black holes billions of light years away. That distance is critical. The farther waves travel, the more spacetime's expansion affects them, amplifying phantom energy's fingerprints. There's another tantalizing possibility. Phantom energy might warp gravitational waves unevenly. Just as light bends around massive objects, creating cosmic mirages, phantom energy could distort gravitational waves in ways that reveal its true nature. Some models suggest these waves might arrive slightly out of phase, their peaks and troughs misaligned, or exhibit unexpected scattering patterns, like ripples crossing a choppy ocean. These anomalies would be ghostly hints of something far stranger lurking in the equations. Of course, the challenge is distinguishing phantom energy's signal from cosmic noise. The universe is a chaotic place, filled with magnetic fields, interstellar gas, and other gravitational waves that could muddy the data. Scientists will need to compare multiple events, looking for consistent deviations that point to a deeper trend. It's like trying to prove a river is rising by studying thousands of scattered raindrops. Each one tells part of the story, but only together do they reveal the flood. If gravitational waves do betray phantom energy's presence, the implications would be staggering. Unlike light, which can be absorbed or scattered, gravitational waves pass through nearly everything unimpeded. They're the universe's messengers, carrying information from the most violent and distant events. If those waves bear signs of phantom energy, it would be as close to a direct detection as we're likely to get. But if they show no trace, the case for phantom energy weakens, forcing theorists back to the drawing board. Either way, gravitational waves offer something rare in cosmology, a testable path forward. Too many theories about the universe's fate remain trapped in the realm of equations, untouchable by observation. But here, at last, is a way to probe the darkness directly. The next time two black holes collide in the distant cosmos, their gravitational waves might carry more than just the story of their own demise. They could whisper the universe's final secret, a warning etched into the very fabric of spacetime. Quantum fluctuations, those ghostly flickers of particles appearing and vanishing in empty space, might seem like a footnote in the grand story of the cosmos, but they could hold the key to phantom energy's destructive potential. These fleeting bursts of matter and antimatter, predicted by quantum field theory, aren't just mathematical quirks. They're proof that the vacuum of space is anything but empty. Every cubic centimeter of the universe crackles with this subatomic static, a seething foam of energy that defies classical intuition. Now imagine that same chaotic dance interacting with phantom energy, amplifying its repulsive force like a microphone feeding back into a speaker. The result? A runaway effect where quantum whispers become cosmic screams, tearing spacetime apart faster than anyone predicted. This idea hinges on a bizarre twist of quantum mechanics. Normally, particle-antiparticle pairs annihilate almost instantly, their energy borrowed from the vacuum and repaid before nature notices the debt. But phantom energy could disrupt this delicate balance. If its repulsive force stretches space rapidly enough, those virtual particles might not have time to vanish, effectively becoming real. Picture a magician's trick where the disappearing act fails, except instead of rabbits, it's the raw energy of creation itself, flooding the universe with extra repulsive power. The more space expands, the more particles materialize, driving expansion even faster in a nightmarish feedback loop. The math behind this scenario pushes physics to its breaking point. Quantum fluctuations obey uncertainty principle, which allows particles to borrow energy briefly so long as they return it quickly. But phantom energy's exponential expansion could stretch that repayment deadline, turning temporary quantum loans into permanent cosmic liabilities. Some models suggest this could warp the very definition of empty space, transforming the vacuum into an unstable medium where the rules of quantum field theory no longer apply. It's like discovering the floor beneath you isn't just uneven, it's dissolving into quicksand. Yet proving this connection remains a monumental challenge. Quantum fluctuations operate on scales a billion times smaller than an atom, while phantom energy's effects span billions of light years. Bridging these extremes would require experiments of unimaginable precision, perhaps particle colliders powerful enough to recreate conditions last seen moments after the Big Bang, or space-based detectors sensitive enough to measure phantom energy's gravitational shadow on individual atoms. Until then, the idea remains a tantalizing what if, a thread connecting the infinitesimal to the infinite. What makes this theory so electrifying isn't just its apocalyptic implications. It's the way it forces physics to confront its own limits. Quantum mechanics and general relativity, the twin pillars of modern science, clash violently at these extremes. Phantom energy amplified by quantum fluctuations could be the stress test that finally reveals which theory bends or breaks. Will we uncover new layers of reality, or hit a wall where our equations simply fail? The answer might determine whether the universe's fate is knowable, or if some mysteries are written in a language we'll never decode. For now, all we have are the whispers of particles in the void, hinting at either a revelation or a reckoning. Cosmic holography theory paints the universe as a vast, shimmering illusion, a three-dimensional projection encoded on a two-dimensional surface at its edge, like a movie screen wrapped around reality. This isn't science fiction. It's a serious hypothesis born from black hole physics, where the information swallowed by singularity seems to linger on the event horizon like a cosmic fingerprint. If true, every star, galaxy, and particle in our universe might just be data etched onto some unfathomable boundary, a hologram where depth is an elaborate trick of quantum entanglement. But phantom energy throws a wrench into this elegant idea. If space stretches violently enough to shred atoms, what happens to the information they carry? Quantum mechanics insists information can never be truly destroyed, only scrambled. Yet the Big Rip threatens to vaporize it entirely, leaving holography's delicate code in tatters. The stakes couldn't be higher. In a holographic universe, losing information isn't just about forgetting where you left your keys, it's about reality glitching at its core. Imagine a hard drive cracked in half mid-save, corrupting the files that define existence. Black holes already tease this paradox. When matter falls in, its information persists on the event horizon's surface, preserving the universe's ledger. But phantom energy's endgame doesn't offer such neat accounting. As spacetime rips, even horizons would dissolve, erasing the cosmic hard drive before anyone can back it up. Theoretical physicists shudder at the implications. If information vanishes, the holographic principle collapses, and with it, our best hope of unifying quantum mechanics and gravity. This dilemma has spawned wild solutions. Some theorists suggest phantom energy might expose hidden layers of reality, like a hologram peeling back to reveal the projector. In these models, the universe's true structure isn't just encoded on its boundary. It's woven into higher dimensions, with phantom energy acting as a cosmic X-ray, exposing the scaffolding beneath. Others propose that information isn't lost but transformed, scrambled into a language so alien we'd need new physics to decode it. The most radical idea, the hologram isn't static. As phantom energy stretches space, the universe's screen might reconfigure itself, pixel by pixel, to preserve information in ways we can't yet imagine. Yet for all the creativity, the core mystery remains. If the universe is a hologram, its stability relies on perfect harmony between bulk and boundary. Phantom energy disrupts that balance, pitting the holographic principle against entropy in a winner-takes-all duel. The outcome could rewrite not just cosmology, but the nature of existence. Are we living in a simulation that glitches when stretched too thin? Or is holography itself an incomplete metaphor? A ladder will need to kick away once phantom energy forces us to climb higher. The answers might lie in the static between theories, waiting for the next genius or the next cosmic catastrophe to bring them into focus. Neutrinos are the universe's ultimate ghosts, particles so elusive they can pass through light years of lead without a single collision. Billions stream through your body every second, leaving no trace, no ripple, no hint of their presence. Yet these phantoms might be hiding secrets about phantom energy, the very force that could tear reality apart. Recent experiments have spotted something strange, neutrinos behaving in ways that defy the standard model of physics. Some oscillate between flavors faster than expected, as if an unseen hand is tweaking their properties. Others arrive with energies that don't quite match predictions, like echoes from a shadow dimension. Could these anomalies be phantom energy's fingerprints, warping the fabric of spacetime so subtly that only neutrinos, particles barely tethered to reality, can feel it? The connection isn't as far-fetched as it sounds. Neutrinos are uniquely sensitive to the universe's hidden layers. Unlike photons or electrons, which interact constantly with matter, neutrinos slip through the cosmic background almost untouched, carrying information from the most extreme environments, black hole jets, supernovae, even the Big Bang's afterglow. If phantom energy is stretching spacetime unevenly, neutrinos might be the only particles light enough to wobble in response. Picture a spiderweb trembling at the slightest breeze while heavier objects stay still. Experiments like IceCube in Antarctica and SUPER in Japan have spent decades mapping these tremors, sifting through petabytes of data for anomalies that could rewrite physics. One tantalizing clue comes from sterile neutrinos, a hypothetical fourth flavor that doesn't interact via any known force except gravity. Some theorists suggest phantom energy could amplify their effects, creating neutrino mirrors where particles flicker in and out of our reality. Others propose that neutrinos might leak into extra dimensions, their disappearances hinting at phantom energy's grip on hidden folds of spacetime. The challenge, proving it. Neutrino detectors are already marvels of engineering, buried deep underground or under ice to shield from cosmic noise. Yet even these labs struggle to pin down the particles' quirks, leaving room for debate over whether anomalies are breakthroughs or measurement errors. What makes this hunt so urgent is the scale of the stakes. If neutrinos are truly reflecting phantom energy's influence, they could offer an early warning system, a cosmic canary in the coal mine. Their odd behavior might escalate as spacetime's expansion accelerates, giving us decades or centuries to prepare, if prepare is even possible. Alternatively, the anomalies might be red herrings, statistical blips in humanity's stubborn quest to find patterns in the dark. Either way, neutrinos remind us that the universe's deepest truths often lurk where we least expect them, whispered by particles that barely exist at all. The question isn't just whether we're listening, it's whether we'll understand what they're trying to say before it's too late. The phantom energy dilemma is more than a scientific curiosity. It's a mirror held up to the limits of human knowledge, reflecting how much we've yet to learn about the cosmos. Whether the Big Rip becomes reality or fades into the footnotes of physics, the very fact that we're having this debate reveals something profound. A century ago, scientists believed the universe was static and eternal. Today, we're grappling with the possibility that space itself could one day shatter like glass. That shift isn't just progress, it's a testament to our refusal to accept easy answers, even when the truth unsettles everything we thought we knew. What makes phantom energy so compelling isn't just its apocalyptic potential, it's the way it forces us to confront the boundaries of our understanding. Every equation, every telescope observation, every supercomputer simulation is a step into uncharted territory where the rules we rely on might bend or break. This isn't failure, it's discovery in its form. The greatest breakthroughs in science have always come from staring down the impossible, from reimagining gravity to revealing an expanding universe. Phantom energy could be the next frontier, a puzzle that reshapes cosmology as radically as those revolutions did. Yet there's a quieter lesson here too. The universe doesn't owe us clarity. Its mysteries won't unravel just because we're curious. But that hasn't stopped us from trying. From ancient stargazers tracking celestial motions to modern physicists hunting for phantom energy's fingerprints, the drive to make sense of the cosmos is woven into human DNA. Even if the Big Rip never comes, the questions we've asked while chasing it, about dark energy, quantum fields, the nature of time, will echo through science for generations. So where does that leave us? Not in despair, but in awe. The universe might be fragile, but our curiosity is indestructible. Every anomaly in the data, every unexplained flicker in the night sky is an invitation to look deeper. Future telescopes, experiments, and theories will keep probing the darkness, whether it hides phantom energy or something stranger still. And as long as we keep asking, keep wondering, keep reaching for the next piece of the puzzle, we're honoring the most human impulse of all, to stand under the stars and dare to understand them. The cosmos may be vast and indifferent, but our quest to know it, that's anything but small.